Okay, so this is an example on conservation momentum for inelastic collisions, where the kinetic energy is not conserved, although the momentum would be conserved as the two objects would stick together. So let's read the problem. A block of mass m1 travels horizontally with constant speed v0 on a plateau of height h until it comes to a cliff. A toboggan of mass m2 is positioned on level ground below the cliff as shown above. The center of the toboggan is a distance d from the base of the cliff, and a determine d in terms of v0, h, and g, so that the block lands in the center of the toboggan. So let's just draw this trajectory real quick. What's going on? So this block is being launched horizontally with the initial velocity in x direction v0. So the block would somewhat go like that. And let's go ahead and determine our directions. So we can say that the positive direction is the left, and x direction is left, and positive y direction is the top. And so now basically this is a kinematics problem that we're going to be doing here with our set values. So the block is going to land here, meaning that it travels a distance, d, and it is given an initial velocity, and we have some other values. So now if we go ahead and see what we have in terms of our values, we know that in our x direction, delta x would be d, and then the acceleration in any projectile is 0, and its initial velocity is v0, but we do not know the time. So we can use the equation delta x is equal to v initial x times t plus half ax t squared. Since the acceleration is 0, but we can go ahead and cancel that term out. And then plugging in our values, we get d is equal to v0 times t. And now we don't really have any variables we're not allowed to use this t. So now what we can do is we can go ahead and set up a similar equation, except in the y direction. Since the time is constant for any projectile in the x and y direction, we can consider this as like a bridge between these two that connects them together. So still in this y direction, we don't know the time. We know the acceleration due to gravity is negative g, and we know that the displacement in the y direction would be negative h, since the block would be dropping a distance h. And we know that the initial velocity in the y direction is 0, since it's traveling only horizontally initially. So now we can set up the same equation as above, delta y equal to v initial y times t plus half ay t squared. And since the initial velocity in the y direction is 0, we can go ahead and plug in our values. So negative h is equal to half negative g t squared, so we can cancel those negatives out. And now isolating t, we get t squared is equal to 2h over g, and taking the square root of both sides, t is equal to square root of 2h over g. So now we have our time, and in the variables that we're allowed to use, h and g, the fundamental constant g, and now we can go ahead and plug that back in to our original equation. So d is equal to v0 times 2h over g. That's our final answer. And what they wanted us to find is determine d in terms of v0, h, and g. Thank you. Okay, so this is part B. Part B says the block sticks to the toboggan, which is free to slide without friction. Determine the resulting velocity of the block and the toboggan. So from just reading this problem, we can say that since the block sticks to the toboggan, we can say that this is an inelastic collision between the block and toboggan. And it also says that the block is free to slide without friction, so there's no frictional force. And we're trying to find the resulting velocity of the block and toboggan, so you can say that they would be moving together in the left direction. So before we do this, we want to define what our system is before doing any momentum conservation problems. So we have this toboggan, and then we have a block over here right before it hits it, right? So when the block hits the toboggan, since there would be no horizontal force provided, since there's no friction, then the only forces that would be provided from the toboggan to the block would be a vertical force. And since we're defining our system as this, we can say that the net force acting on the system would be 0 in the x direction, we're saying that the net force is 0. Although in the y direction, there might be some normal force over there. But we don't care about that because we're trying to find the resulting velocity in the left direction. So we can say that the net force in the x direction is 0, and thus we can conserve our momentum in the x direction. The initial velocity in the x direction will be equal to the final velocity in the x direction as well. So now now that we have our equation set up, now we can go ahead and solve this. So our initially right before the block hits the toboggan, it's only the block that is moving with the velocity in the horizontal direction. And since we're defining our positive x direction to be left, we can go ahead and say that since it's a projectile, it would have a velocity v0 throughout its trajectory. So we can say since momentum is defined as mv, and we are given that the block of mass m1 is its mass, so m1 times v0. So this is our initial momentum. And now it's saying that the block and the toboggan are stuck together when they hit. So now we can say that they're just one object. So we can go ahead and say that their combined mass would be m1 and toboggan of mass m2, so m1 plus m2. And we're trying to find this resulting velocity. So we can say times vf as a resulting velocity. And now this is a simple isolation problem. So we can go ahead and isolate vf by dividing both sides by m1 plus m2. So vf would be equal to m1 times v0 divided by m1 plus m2. So this would be our resulting velocity of the block and the toboggan. So the main thing to take away from this problem is that when you're doing any momentum conservation problems, it's always important to set up your system and just decide what forces are acting on the system and in what direction the momentum would be conserved. And as in this case, the momentum would be conserved in the x direction, and all these internal forces just cancel out. Thank you.